Get ready to revolutionize the world of natural language processing with MoEBERT, the innovative model that's about to change the game. In this video, we'll dive into the world of pre-trained language models, explore the limitations of traditional methods, and introduce MoEBERT, the mixture of experts model that's set to outperform its competitors. So, buckle up and let's get started. Hello and welcome to today's explanation of the research paper MoEBERT from BERT to Mixture of Experts via Importance Guided Adaptation. This paper proposes a new approach to compressing pre-trained language models, which are typically very large and computationally expensive to use. The authors of this paper start by explaining that pre-trained language models have been shown to be very effective in many natural language processing tasks, such as natural language understanding and question answering. However, these models can contain hundreds of millions of parameters, which makes them difficult to use in real-world applications where latency is a concern. The authors then discuss the problem of model compression, which is the process of reducing the size of a model while maintaining its performance. They explain that existing methods for compressing pre-trained language models, such as knowledge distillation, can be effective but often result in a significant drop in performance. The authors propose a new approach called MoEBERT, which uses a mixture of expert structure to increase the model capacity and inference speed. They initialize MoEBERT by adapting the feed-forward neural networks in a pre-trained model into multiple experts, and then use a layer-wise distillation method to train MoEBERT. The authors validate the efficiency and effectiveness of MoEBERT on natural language understanding and question-answering tasks, and show that it outperforms existing task-specific distillation algorithms. For example, they show that MoEBERT outperforms previous approaches by over 2% on the MLI mismatched dataset. On the page 2, the author is explaining the concept of mixture of experts MoE models. They are explaining that a layer of a MoE model consists of an attention mechanism and multiple feed-forward neural networks FFN in parallel. Each of the FFN is called an expert. During training and inference, an input adaptively activates a fixed number of experts, usually 1 or 2. This property facilitates compression without reducing model capacity. However, MoE models are difficult to train from scratch and usually require a significant amount of parameters. The author is also explaining that MoEBERT, which is the proposed model, incorporates the MoE structure into pre-trained language models for fine-tuning. This model can speed up inference while retaining the representation power of the pre-trained language model. The author is explaining that the expert structure is incorporated by adapting the FFN in a pre-trained model into multiple experts. For example, the hidden dimension of the FFN is 3072 in byte base, and it is adapted into 4 experts, each with a hidden dimension of 768. The author is also explaining that MoEBERT uses an importance-based method to adapt the FFN into experts. This method is based on the importance score, which is a measure of how important each neuron is in a model. The author is explaining that when initializing MoEBERT, they share the most important neurons among the experts, and the other neurons are distributed evenly. This strategy has 2 advantages. First, the shared neurons preserve the performance of the pre-trained model. Second, the non-shared neurons promote diversity among experts, which further boosts model performance. On the page 3, the author explains that the MoE model is a mixture of experts, where T is the activated set of experts with T equals K, and pi is the weight of expert I. The author explains that different approaches have been proposed to construct T and compute pi. For example, Shazir et al. 2017 take pi equals softmix at WGI, where WG is a weight matrix. However, this approach suffers from load imbalance, where WG collapses such that nearly all the inputs are routed to the same expert. The author explains that existing works adopt various ad hoc heuristics to mitigate this issue, such as adding Gaussian noise direct. 3. Limiting the maximum number of inputs that can be routed to an expert, imposing a load balancing loss, and using linear assignment. The MoE model is a mixture of experts, where T is the activated set of experts with T equals K, and pi is the weight of expert I. The author explains that different approaches have been proposed to construct T and compute pi. For example, Shazir et al. 2017 take pi equals softmix at WGI, where WG is a weight matrix. However, this approach suffers from load imbalance, where WG collapses such that nearly all the inputs are routed to the same expert. The author explains that existing works adopt various ad hoc heuristics to mitigate this issue, such as adding Gaussian noise direct. 3. Limiting the maximum number of inputs that can be routed to an expert, imposing a load balancing loss, and using linear assignment. On the page 4, the author explains how to adapt the pre-trained BERT-based model into a mixture of experts MoE model. The author uses the importance-guided adaptation method to adapt the model. The importance score is calculated for each neuron in the model, and the neurons are sorted in ascending order according to their importance scores. The most important neurons are shared between the experts, and the least important neurons are discarded. This method reduces the number of effective parameters in the model, resulting in a ×2 speedup. The author also explains the layer-wise distillation method to remedy the performance drop caused by adapting the pre-trained model to a MoE model. The layer-wise distillation method uses the teacher model to guide the student model to learn the correct output for each layer. The distillation loss is calculated as the mean squared error between the teacher's layer output and the student's layer output. On the page 5, the author explains the model training process of MoEBERT. The author employs a random hashing strategy to train the experts. This means that each token is pre-assigned to a random expert, and this assignment remains the same during training and inference. The training objective is to minimize the cross-entropy loss between the model's output and the true label, plus a distillation loss term. The distillation loss term is used to encourage the model to mimic the behavior of a pre-trained teacher model. The author also explains that the training data set D and samples X, Y are used to calculate the training objective. The training objective is a combination of the cross-entropy loss and the distillation loss term. The cross-entropy loss is used to measure the difference between the model's output and the true label, while the distillation loss term is used to measure the difference between the model's output and the output of the pre-trained teacher model. In experiments, the author uses the Hugging Face Transformers codebase to implement the MoEBERT algorithm. The experiments are conducted on NVIDIA 100 GPU. On the page 6, the author presents the experimental results of the proposed MoEBERT model on the GLUE development set. The results are shown in Table 1. The table compares the performance of MoEBERT with several baseline models including BERT, DistilBERT, TinyBERT, MiniLM-Vaughan, MiniLM-V12, CodeIR, PKD, and BERT of thesis. The results show that MoEBERT outperforms all of the baseline models in 6/7 tasks. The authors also observe that task-agnostic distillation methods generally perform better than task-specific ones. For example, the best-performing task-specific method, BERT of thesis, has an accuracy of 68.2 on the RTE dataset, while the accuracy of MiniLM-V12 and TinyBERT is greater than 72. MoEBERT, on the other hand, achieves an accuracy of 74.0 on RTE without any pre-training, indicating the effectiveness of the MoE architecture. The authors also present experimental results on two question-answering datasets, SKD1.1 and SKD-V12.0. The results are shown in Table 2. The table compares the performance of MoEBERT with several baseline models including PKD, MiniLM-Vaughan, and MiniLM-V12. The results show that MoEBERT significantly outperforms all of the baseline models in terms of both evaluation metrics, exact match EM and Vaughan. The authors also conduct an ablation study to examine the effect of expert dimension and the number of experts on the model performance. The results are shown in Figure 2. The figure illustrates that as the expert dimension increases, the model performance improves, and as the number of experts increases, the model performance also improves. On the page 7, the author is presenting the experimental results of the proposed MoEBERT model on various tasks. The author is comparing the performance of MoEBERT with other pre-trained language models such as BERT-based, DistilBERT, TinyBERT, MiniLM-Vaughan, and MiniLM-V12. The results are presented in Table 2, which shows that MoEBERT outperforms all the other models on SKD1.1 and SKD-V12.0 tasks. The author is also presenting the results of an ablation study on MNLI in Figure 2. The figure shows the average accuracy of MNLI-M and MNLI-MM for different settings of expert dimension, number of experts, and shared dimension. The results indicate that the default settings of expert dimension 768, number of experts 4, and shared dimension 512 are the best. The author is also examining the effectiveness of layer-wise distillation in Table 3. The results show that removing the distillation module significantly drops the model performance, indicating the importance of distillation in fine-tuning the adapted model. The author is also analyzing the effectiveness of importance-based adaptation by experimenting with two different strategies, randomly splitting the FFN into experts and adapting and sharing the FFN according to the neuron's importance scores. The results show that the importance-based adaptation strategy outperforms the random strategy. On the page 8, the author discusses the adaptation, distillation, and routing methods in MoEBERT. The author explains that MoEBERT is trained using a layer-wise distillation method, where distillation loss is added to every intermediate layer. The author examines two variants, only distilling the hidden states of the last layer and distilling the hidden states of every other layer. The results show that only distilling the last layer yields unsatisfactory performance, while distilling the hidden states of every other layer obtains similar results compared to the layer-wise distillation method. The author also discusses different routing methods in MoEBERT. By default, the author uses a random hashing strategy to route input tokens to experts. However, the author examines other routing strategies, including sentence-based routing with a trainable gate and a balanced hash list. The results show that the sentence-based routing strategy can significantly reduce communication overhead in MoE models and is advantageous for inference. The author also compares the inference speed of BERT, DistilBERT, and MoEBERT on the SST-2 dataset. The results show that MoEBERT is slightly slower than DistilBERT, but significantly faster than BERT. The author also discusses compressing larger models. The author explains that task-specific distillation methods do not require pre-training and can be easily applied to other model architectures and sizes beyond BERT base. The author compresses the BERT large model by adapting the FFN in BERT large into 4 experts, such that each expert has a hidden dimension of 1024. The author shares the top -512 neurons among experts according to the inverse importance. On page 9, the author presents the results of the proposed method, MoEBERT, which uses a mixture of expert structure to distill pre-trained language models. They demonstrate that MoEBERT can speed up inference by adapting the feed-forward neural networks FFN in a pre-trained language model into multiple experts. The author also presents the experimental results on the RTE and MNLI, which show that MoEBERT behaves on par or better than BERT large in all of the experiments. This means that MoEBERT is able to retain the model capacity of the pre-trained model, unlike existing approaches that limit the representation power of the compressed model, resulting in unsatisfactory performance. The author also explains that they use an importance-based method to identify and share the most important neurons in the FFN among the experts. This is done to adapt the FFN into experts. Additionally, they propose a layer-wise task-specific distillation algorithm to train MoEBERT. The results show that the proposed method outperforms existing distillation approaches. The author also mentions that they do not find any ethical concerns in their experiments, as they use publicly available data and models and build their algorithms using public code bases. Thank you for watching this video on a research paper MoEBERT from BERT to mixture of experts via importance guided adaptation. In this paper, the authors propose a new approach to compressing pre-trained language models, which are typically very large and computationally expensive to use. They achieve this by adapting the feed-forward neural networks in a pre-trained model into multiple experts, and then use a layer-wise distillation method to train the model. The authors validate the efficiency and effectiveness of MoEBERT on natural language understanding and question-answering tasks, and showed that it outperforms the existing task-specific distillation algorithms. For example, they show that MoEBERT outperforms previous approaches by over 2% on the MNLI mismatch dataset. In conclusion, MoEBERT is a powerful approach to compressing pre-trained language models while maintaining their performance. It has the potential to be used in real-world applications where latency is a concern, such as in chatbots, virtual assistants, and other natural language processing applications. If you found this video helpful, please like, subscribe, and share it with your friends and colleagues. Also, if you have any questions or comments, please feel free to leave them in the comments section below. And if you're interested in learning more about other research papers or AI-related topics, please let us know in the comments section. We'd be happy to create more videos on topics that interest you.